Hello, friends. Today in this session, we will discuss about software delay. So, how to generate a software delay. Using that, we are going to develop a counter program. So, this is a BCD counter. So, let me explain you the program first. So, these three instructions by now you should be familiar with. It is common line for all the programs. So, we are starting the program from 30H, and we have initialized the value of accumulator to 00. Then call delay. Delay is a function. Basically, we are using absolute call to call a delay. So here we have a delay program written. Okay. Here, if you observe, three general purpose registers are used: R1, R2, and R3. Initialized to different values. You can initialize to any value. No issues with that. All the registers are of 8 bits, so you can have up to FF is the maximum value we can have. So you can initialize any value within that 0 to FF. Okay. So now R3, what we have here. So if you observe, here we have one more instruction called DJNZ, that is decrement and jump if not 0. So now what it does, it will decrement the R3 content and it will check if it is not 0, then it will jump to the label given. Now here, instead of a label, I have given a dollar symbol. So this is a, in some cases you might come across this. So I just thought of telling you how it works. When we want to give a label to the same instruction like this, what we are given here, right? We are writing the label here and looping back to the same instruction. Whenever we want to do that, we can use a dollar symbol for that. So it will loop back to the same instruction. So this instruction is going to execute till R3 becomes 0. That means it is up to 255 times it is going to execute. 255 times it will execute. Okay. So that's a decimal value. In hex it is a 0FF. So this will execute 255 times. Which one? This one will execute 255 times. And DJNZ is a 2-byte instruction. That means it's a 3-byte instruction in the memory, but it will take two machine cycles to execute. So it will be taking two machine cycles for the execution. Okay. So based on that, we will be able to calculate the delay generated by that instruction. Now for each machine cycle, in standard microcontroller operating at 11.0592 megahertz, the machine cycle period is equal to 1.085 microsecond. 1.085 microsecond. That means that is one machine cycle period. So once we know this machine cycle period, then we can calculate the delay generated by the particular instruction. Similarly, you have a next loop, which is a R2 loop. Now R2 loop has a label and it will be going back here. Now if you observe, this is also executing 255 times. That is R2 loop. Now, for every R2 decrement, it will again go back and reinitialize R3. So that means it's going to execute another 255 times. So 255 into 255 into 2. Okay, so this will be executing 255 times. Then we have another loop, that is R1 loop. So that is label is decrement 1. So this will reinitialize both R2 and R3. So the value for the R1 is 35. So again we will multiply by 35. This is the number of machine cycles. This is also multiplied by 35. This is also executing 35 times. Okay. So like that, depending on the looping, we can calculate how many times a particular instruction is being executed. And then once we have the number of machine cycles consumed for the execution, Then we can multiply that with 1.085 to calculate the actual delay generated by the program. Now coming to the main program, once you this function is executed, it's coming back and adding a to 99. A is 00. So initial value is 0 plus 99, it will become 99. Remember, this is a down counter. If we want to up counter, all you have to do is just increment, because that's very simple. But in the down counter, we have uh, very peculiar operation of DA instruction. So I thought I will consider this. So now decimal adjust. What it will do is it will add is we know that the addition after addition the value what we get is a hexadecimal value. Now we want to adjust that to decimal value. To do that adjustment, this instruction is used. And remember, this DA instruction can be used only after add instruction. We cannot use it anywhere else. This instruction should be used immediately after add instruction. Only then it will work. Okay. So it will convert our hexadecimal number to a proper BCD number. Then we have GNZ back, that is looping back to the this label. So it will be continuously executing. Okay. Now let's see how does it actually work. So we don't have any errors here or a warning. Now let's go to debug mode. Okay. So in the debug mode, already we have discussed about disassembly. You can check it every time you want to understand that. You can see here. So how much memory it will take, everything will be shown here. Okay. Then here we will see how exactly program is working. So now to observe the changes happening in the accumulator, that is a counting whatever happens in the accumulator. Either we can check it here, the changes what's happening, or we have one more provision, that is in the watch window. In the watch window, so I'll just show you. So if you go to view, we have a watch window here. If I click on watch window, the window will appear. So here I can enter any register I want. Here I have given a value a accumulator. So it will reflect the value of accumulator here. Now the accumulator value is 00, so it is showing 00. Like that, as the accumulator value increments, decrements, it's going to show the changes in that. Now let's run the program. Now you can see that it is decrementing from 99. Of course, you can see some characters just in front of that, and that character is a reflection of considering this as a ASCII value. So this is considered the ASCII value, and the character of that ASCII value is shown in front of that. See, now it has come to 00 and it has stopped. Now if I stop it and run it again it will start from 99. Okay, you can see here again it is starting from 99. It start decrementing. Okay, so this is how the BCD counter works. So most important thing in the BCD counter is using the die instruction. This is decimal adjust. So basically what it does, whenever we add two numbers, if the number after addition, if any nibble value becomes greater than 9, that is if it becomes a hexadecimal number, or it generates a carry, in both the cases it will add 6 to that particular nibble. After addition, it will you will get the equivalent BCD. Okay, whenever we add two numbers, if the number is generating a carry or the result is greater than 9, in both the condition, 6 is added to that particular nibble. That's what this die instruction do to adjust the BCD value. Okay, so that's it for this video. Let's come out of debug mode. Okay, uh, thank you. Have a good day.